Hilbert Space. Okay. Okay, thank you. And obviously you define quantum operators, and new things will be variance, calculating variance of operators. One usually, I mean, we'll do that. And the third part, of course, is showing presenting results. It will mainly concern quantization of considering eigenproblem for Kretschmann operator. And then I will talk about generalization, conclusions, next steps, prospects, okay? So, as everybody knows, Schwarzschild spacetime was probably one of the first spacetimes, let's say, discovered gravitational physics. It was done by Karl Schwarzschild and almost at the same time by Johannes Drost in 1916, very early. In my talk, I will, for quantization of that spacetime, I will only need explicit form of spacetime metric. And also, this is important because in our further plans, we also are able to, if you give me an explicit form of metric, we will have method of quantizing a given system, okay? Now novelty. Novelty would be a quantization of not only spatial, but also temporal coordinates. So in a sense, it touches the problem of time at quantum level. You know, there will be a special talk devoted to this issue. It will be seminar, a seminar done by, where is it? By, just a second, where is it? By Klaus Kiefer on the April 8th, okay? It will be devoted to that. I invite him to give a review article. But anyway, in this talk, I will just present our idea of, let's say, defining time at quantum level. And a rationale for this will be that distinction between spaces time violates diffeomorphism invariance. So due to that, we quantize not only temporal, but also not only spatial, but also temporal coordinates. So in a sense, we are quantizing time, let's say, roughly speaking. Aim of my talk is the following, that I would like to present, I think, simple but powerful quantization method, not very common to this audience. Of course, presenting the idea of time quantization. No, yeah, of course, its application of this too would be, you know, showing that singularity of Schwarzschild spacetime can be avoided at quantum level. That's roughly speaking the plan. Okay, I mean its introduction. Okay, now let me remind you that a Schwarzschild metric in the so-called Schwarzschild coordinates has this form. Everybody knows this. So let me remind you that T is called time coordinate, R is radial coordinate, it is written, measured as the circumference of the sphere centered around isolated object. M is parameter, mass parameter of this isolated object. Theta and phi are angle coordinate of sphere, okay? This is for R greater than 2m, just, I mean, names, time and the coordinate. As you know, as m goes to 0, it just turns into Minkowski metric. If R goes to infinity, it is to Minkowski metric. Schwarzschild spacetime is asymptotically flat. All this is known. but I need it for quantum steps. Okay, so that's why I'm recalling this ideas. Now, singularities. If you look at the metric, you will say, well, there's something wrong going when R approaches to M, because this is 0 and this goes to 0. So it means this factor goes to infinity. So you may think that there is something special at R equals to M. I mean, there is singularity, but that it's not true. This is just coordinate singularity. We call it, it corresponds to event horizon for more sophisticated models, but here it is called event horizon. And this is coordinate singularity because there are other coordinates in which metric is regular at R equals to N. For instance, Eddington, Wittgenstein, Penleve-Gullstrand, and maybe best known Kruskal-Sekeres. These are extensions of this manifold spacetime. Okay. Now, curvature invariants. I mean, something that tells you what is gravitational singularity. You should use curvature invariants. In the case of Schwarzschild, the first Ricci scalars equals 0. The first non-vanishing but quite sophisticated is Kretschmann. Is Kretschmann scalar. So here is explicit form of it. So you can see that it blows up as R goes to infinity. Okay. Now, for M positive, we have the horizon, so that the model has covered singularity. I mean, it is black hole. So this R2 equals to M set specifies one-way membrane. Okay. However, for negative M, which is also considered, for instance, in Piotr Hruściel's textbook, Gravity, there is no event horizon, because look, if M is negative, I mean, all these coefficients are well defined, no problem. So if M is negative, there's no horizon, and this case is called naked singularity. We say that space-time has naked singularity. There are no horizons. And now let me make a remark. You can maybe wonder whether it is physical or not. Well, I would say there is a series of paper by Pankaj Joshi and his co-workers, in which they examine cases, isolated objects with naked singularities. Because, you know, these objects can also have accretion disk and jets, but there are ways to make distinction between observationally between black hole and object with naked singularity. But it is interesting theoretically because, you know, in case of naked singularity, if this is real, if these objects are real, they, you know, getting information from such objects, isolated object, may be very useful in construction of quantum gravity, because, you know, horizon may screen some information. So it's very, I mean, promising for theoretical, from theoretical point of view. Okay. Now, let me just now define for you configuration space, which I said is something new. Well, it is defined here as the half plane, which is made of points T and R. So these are okay. This angles are not interesting for us, because they don't enter the expression for Kretschmann scalar. So we are not going to quantize them. We are going to quantize T and R. So the rest of my talk will be devoted to quantization of Schwarzschild with naked singularity. Okay. Now, let me just say what I mean in this, for the purpose of this talk, by quantization. So, well, I will mean quantization of observables defined on that configuration space, which I defined a second ago. So, as usually, what we ascribe self-adjoint operators, trying to ascribe self-adjoint operators acting on some Hilbert space. We calculate expectation values of quantum observables. Here we'll also calculate variances of quantum observables, okay? So this is what I will mean by quantization for the purpose of this talk, okay? And considered observables will be elementary observables, I mean time in the radial coordinates. You know, I've forgotten to tell you that for M negative, the coordinate r is all the time space-like, and t coordinate is time-like. That's important somehow. It simplifies this quantization procedure. And this is one of the reasons we started quantization and Schwarzschild with naked singularity, because these things are well defined. As I said, we will quantize both temporal and spatial coordinates. And we treat them on the same footing. Yes. The composite observables, which we consider to be Kretschmann scalar, okay? So now I begin the defining a quantization process. It is based on the fact that since our configuration space is a half plane, it can be identified with the affine group, namely in that way that we ascribe group structure on this configuration space. In that case, in that way, that space, configuration space, becomes a group, okay? And in this case, a affine group. Now, that's important thing that you can do this ascribing group structure to the space in many ways, I would say. And the way you describe is called group parameterization. You know, actually there are two parameterizations which are used commonly. The first one is used by us. The second one is used by Jean-Pierre Gazo's and people around for a long time. But I was also using this parameterization when I started my adventure with coherent state quantization. It is, you know, it's my first paper with Jean-Pierre Gazo, done in 2003, and it was devoted to asymptotic coherent state quantization of a particle in digital space. So, and we are using this parameterization, okay? So I would say that, when I came back to this method of quantization after, you know, quantizing cosmology by loop quantum, loop quantum approach, I came to quantize, you know, in 2014, I came back to quantization, and we started using this prescription. So this was a series of paper where I managed to encourage Jean-Pierre Gazo and other people around to begin quantization, to applying coherent state quantization seriously to gravitational systems. It was 2014 until 2017 when we started using the first polarization, but with different people, let's say. But in 2020, we compared both methods. Results of using this two different parameterization. These are two papers.
Can I ask a question?
Sure. Go ahead.
Just a second.
There's some reflection of your voice.
The lecture room, we have to turn off. Okay, not okay.
You should probably turn off another computer. Oh, so let's wait. Let's wait for a second. For a few seconds.
Okay, so can you hear me now better?
Yes, yes, now it's good.
Yeah, so the question is the following. Those variables T and R,
yes.
I guess that they have units of length. So,
yes.
So if you multiply them, then this unit squares, and how can you add it to T again?
Are you talking about this parameterization? Here we define group structure, okay, by this multiplication of two points on this configuration space, okay. So I can do this in this way or in that way.
But Turek is asking about dimensions of these variables.
Yes, but I mean, here speed of light equals 1. All these, I mean, constants are taken to be 1. So I don't mind. I mean, everything is supposed to be well defined.
No. You need some constant of dimension of the length.
Well, I understand that in the first parameterization, this in 5, R has to be dimensionless, hasn't it?
Yes, I would say so. Yeah. I would say I haven't thought about it. So maybe I suggest we come back to that, let's say, at the end, okay? Because at the moment it's something not very important, I would say.
Could I add, they are dimensionless, in fact, because it's hidden this. It is in such units used.
Yes. Thank you, Andrei. Yes, thank you, Andrei. Anyway, coming back to this. But these are not only possible parameterization. In fact, there are many. The interesting thing is that different parameterization lead to unitarily inequivalent quantum theories. This is important. But for instance, we applied both parameterization to the quantization of BK scenario, and qualitatively, you obtained the same result in the sense that in both cases we resolved the gravitational singularity. But you know, the details, of course, would be different. Okay, anyway, I shouldn't spend too much time on this. So in this way, one can ascribe group structure to this, what I call configuration space, okay? Now, let's make next step. So now I'm defining Hilbert space. This is something quite important. And it turns out that a fine group has got unitary irreducible representation realized in this Hilbert space, square integrate functions of half-line with such measure. The unitary representation was found by Gelfand and Neumark in 1947. This is 4 pages paper. I've got this paper in my hand. It's called Unitary Representation of the Group of Linear Transformations of the Straight Line. This is mathematical paper, okay? A further contribution, okay. So, and this representation can be defined in this way with the parameterization 5 on the previous transparency. 5 is this first one, okay? So if you give me a vector from this space, you know, it changes, you multiply argument by R and multiply this by such a phase factor, okay? So this is just this unitary representation. It is defined that way. This important, existence of this unitary representation is important, very important, because it enables quantization, defining states, which are called coherent states, in this Hilbert space, okay, in this way. I take any vector from the Hilbert space. I act with this operator, and I get a new vector. So in this way, I create continuous this continuous mapping from my configuration space to the Hilbert space. And this vector is quite important. I mean, in general, it's not important, but it should have suitable properties depending on purpose. It is called fiducial vector, okay? And in fact, it is a free parameter of this quantization scheme. Choosing, depending on the problem at hand, I choose this fiducial vector just to do some specific calculations. Important thing is, interesting thing is that the space of coherent states is highly entangled in the sense that there are only this scalar product is one. If this coherent, if these states are normalized to one, all others are different from zero. These states are highly entangled. That's something because this space is overcompleted. This space is overcompleted. This peculiarity of this coherent states approach. Okay, it's very important. Now I shift to quantum operators. So since the representation is irreducible, one can show easily that this operator here commutes with all unitary operators. In that is such a case, using Schur's lemma, one can prove that this operator must be proportional to unit operator. Okay, this is coefficient. This coefficient defined here. Okay, it's a number. The only thing is that it should be, finite. This measure here is here. Okay, and this is very important. This is just the heart of describing operators to classical observables. Okay, how can I do that? Well, here is prescription. If you give me a classical observable defined on this configuration space, I can ascribe to it operator defined in that way. So I simply plug this function here inside. Okay, and this is classical. Okay, classical. So in that case, I have no ambiguity in this quantization procedure, and we know that this is common disaster of canonical quantization. Here I don't have this problem. The only thing is just to have this operator well defined. By construction, it is symmetric, already symmetric. Whether it is self-adjoint or not, I mean, it's another story as usual. But anyway, by constructor, it is symmetric. That's important. So at this stage, I have defined for you both Hilbert space, carrier space and operators. Okay. Now, important thing, as I promised, is calculating variance of quantum observables. Let me remind you that by variance, the variance is a stochastic deviation from expectation value of quantum observables. So it determines the smearing of quantum observable in general, okay? And the way to calculate it is shown here. So variance of expectation value is, let's say, if you find the formula, so I should find the expectation value of a square and square this quantity to get variance of the given observables. Now, there is an important circumstance, namely that if I take eigenvalue of a given operator, it immediately, this statement tells that variance of such an operator would disappear, okay? And vice versa. If variance equals 0, it means that this state is eigenstate of my A operator, okay? That's important. It will be important for us. It is even here, written here, okay? Let's go ahead. Now I am approaching, I'm quantizing this most important observable, which is Kretschmann operator, Kretschmann observable, is Kretschmann scalar. And here is a quantum operator ascribed to it. So by using that prescription, which I shown to you a minute ago, okay? It has this form. So we resolve the eigen problem for that operator. It is given here. So it turns out that eigenfunction is a generalized eigenfunction distribution, and eigenvalues are just here. So I can this screen. Sorry, but anyway, eigenvalues are bounded from below. Okay, are bounded from below. This is, let's say, here I have shown you a solution to the eigen problem for this operator. Now, let's move to, okay. Now I am going towards finding variance for that operator. The remark is that.
The question, can I ask?
Sure. Go ahead. Go ahead.
What means the integral on the previous slide?
Yes.
If you have 1 over r to power of 6, so
I mean, this is quite complicated, but I mean, curiously, you should first calculate this object, okay? Mean value of this operator. And this is distribution. Plug it here, and I mean, it's not obvious that the result will be that one. I mean, there's a lot of work behind that. This is only formulation, okay? I'm showing you results. Details, so you can find details in the paper, okay, at the beginning. Okay?
So you can avoid singularity at r equals 0?
No, not yet. Okay. Not yet.
Sorry, could I add something? In 13, first is misprint, that is, angles are not in this direction. It should be operator here in 13, 1 over r power 6. And calculation of this 15, this integral kernel, is between the eigenposition state in this supplementary space on which irreducible representation is built.
Yes.
This is simply a technical thing. Yes. For mathematical things, I can say. To solve the problem, we can do this, solve this problem either in this space on the half line, this S square of half line, or on the affine group. Both should lead to the same, exactly the same result. And sometimes it's easier to calculate on one space, sometimes it's easier to calculate on the second space. Yes, this one is calculated in the first.
Because, thank you, Andrzej. Because these two Hilbert spaces are almost isotropic. Okay. So one can do calculation this in the first Hilbert space on this group Hilbert space. Okay, so this is eigenvalue problem for Kretschmann. Now we shift towards finding the variance of that operator. Before, let me only tell you that expectation value of this T operator and R operator coincide with classical ones. So it's nice, let's say, property of this coherent states, of this parameterization also. And now it turns out that expectation value of Kretschmann is given here. So I have answered to you, Jacek. It is singular, okay? It is singular. Expectation value of Kretschmann is singular, okay? As in the classical case. So it goes up at alpha 0, but it is interesting to calculate the variance. Variance of this operator behaves in this way. It's singular as well, okay? Singular as well. So now maybe it's interesting to see the plot of these two expectation value and the variance. It is here. So you can see that you know, the unit here is the variable here is 1 over r. So here it goes to infinity. In this direction is going to infinity. So you see that expectation value blows up, but variance blows up as well. Okay. So it has interpretation, but namely. Oh, okay. But before giving interpretation, let me show you that we obtained, a similar result in case of using basis in this Hilbert space. Okay, let's say it is here. So expectation, also applying this basis to, we find that expectation value of T operator is this one. So T0 is interpretation of this, okay, here. It's interpretation of this parameter here. And expectation value of R is also proportional to gamma. So we have similar situation to the coherent state, but here the difference is that we have such a factor. But now, sorry, if you calculate expectation value of Kretschmann with this in this basis, you will get the following. So it's again blows up as gamma to 6, and but variance blows up even faster. Okay, and this is let me show you. Remember that this is 6, this is 12. So I will show you that in case of coherent states, we obtained the same, 6 and 12, okay? So we have confirmation. So these results are, let's say, it's confirmation of the results obtained for coherent states. So in both cases, we have the same behavior. Blowing up of expectation value of operator, but also blowing up of variance, okay? So it's time to conclude, because I also want to show you some next steps. So conclusion will be following, that both temporal and spatial variables, first of all, are treated the same footing at quantum level, okay? In gravitational systems, this is the first case we have done that for gravitational system. For non-gravitational system, it is, this procedure was used earlier. Much earlier. In this way, I would say that this is, we propose still another way of quantizing, defining propagation at quantum level, namely by quantization of time variable, okay? And yes, and I would say that quantization, with this, using the quantization of time enabled avoiding gravitational singularity. In this sense, I said that the variance blows up as well. So interpretation is the following, that the state corresponding to gravitational singularity cannot be the eigenstate of the Kretschmann operator. So the probability of finding considered black hole in the singular state is equal to 0. So in that sense, we resolve the singularity of at quantum level of the corresponding to. So I will let's say, so yes, we resolve the singularity of classical level in such a sense, okay? Next item is that let me remind you that we have used only metric tensor in our this quantization procedure. So this procedure can be applied to other isolated systems if you only know metric of a given space-time, okay? Metric of isolated objects. So this is conclusion. And now let me move to showing what will be next steps. So in general, this program is quantization, is called quantization of isolated objects, okay? And in this program at the moment concerns spherically symmetric isolated objects with covered and naked singularities. So let's say we parallel, let's say, work on various models. So what I shown you was Schwarzschild spacetime with naked singularity, but sorry, the one with black hole would be is in the progress. Also, we work on quantizing massive shell, a massive shell which has, so inside of shell we have Piechocki space, outside we have Schwarzschild spacetime, and we quantize this by coherent states approach. And let me tell you that quantizing this by canonical methods would be impossible because Hamiltonian is terribly complicated, okay? But as you may remember, our quantization prescription is such that we are not afraid of non-linear, I mean, of operators which are non-linear, non-polynomial function of elementary variables, okay? This method doesn't care. Here we have also quantized let's say, isolated object which has field non-represented Walker dash inside and Schwarzschild outside. It is commonly known as Oppenheimer-Snyder model. It is done. I did it with my young collaborator from Cologne, Tim Schmitz. Okay, and now we are in progress of quantizing the Metz-Trollmann-Bondi with both naked and covered. It is in progress. And as you can easily guess, what we did for Schwarzschild would be applied to this approach. I think it can be done, and we are just work on that, okay? Next step is trying to, first of all, to construct isolated object which has which are described by Bianchi type space-time. This is not entirely crazy idea because already papers done by people from South America in which they are able to describe isolated objects in terms of anisotropic space-times, okay? So this is not entirely, as I said, crazy. We plan to do that. And obviously, the most interesting would be quantization of or rotating objects, which are of Kerr type, okay? This is our, let's say, aim. And certainly, still next step would be being able to describe a collision of Kerr-like two, let's say, isolated objects. And on the top of that, obviously, well, I mean, this item is, this case is interesting because if we manage to get satisfactory classical construction, we can ask question whether this evolution of this type of isolated object evolves towards a BKL scenario, BKL singularity, because in that case, let's say, helpfully quantizing such an object, resolving that singularity would be resolving, let's say, generic type of singularity. But this is, this is hard problem. These two problems are ahead, okay? So let me make a final remark that obviously, I mean, why do we do this, play this game, namely just to be able to describe compact dynamics of observed compact objects is one thing on one hand. On the other hand, if we have the observational data coming from strong gravitational fields, so they may help us to fix parameters of constructed models, okay? And at the end, I have message, especially addressed to especially young researchers, that the coherent state quantization method is powerful and easy to apply to quantization of gravitational systems. I believe that after this talk, young people would be able to apply these methods to some gravitational systems. You can get familiarity with this method, I would say, within half a day. and for comparison, to get familiarity with, let's say, loop gravity approach needs, let's say, at least half a year, okay? So that's, you know, you can see, so I would like to encourage again, but of course, not only young researchers, but all of you. So thank you very much for your attention.
Thank you. And now we can start questions.
I have question. So
yes, please.
How
yes.
can we apply this method in general case?
What do you mean by general?
No, general metric.
Well, you can't, because general metric, I mean, you don't know. You can only say that. You have to. You can't apply this method if you don't know explicit form of metric. Okay, so you can apply it, I guess, to the cases to known, let's say, metrics of isolated objects. As I said, you know, here it was Schwarzschild. Here is again the known metric. I mean, yes, Friedman, Robertson, Walker. And this metric is known. Lewis-Stallman bond is known. I mean, the Kerr metric is known. So you can't apply it in general, completely in general cases. At the moment, maybe in the future.
But even for these special metrics, the quantization depends on the identification of parameters TR with the group.
Yes.
Dimensional.
Yes, this is a basic thing. To identify either phase space or in this case configuration space with the group, because you know it is based on this existence of this unitary irreducible representation. Otherwise, you wouldn't be able to define coherent states. Yes, something for something.
Okay, thank you.
Could I add a comment also on this?
Sure.
Probably the answer for your question is yes, in the sense that we can do this. It means applying it to general metric in the sense, but not using affine group. This group should be much larger, probably more complicated, based on diffeomorphism, but the diffeomorphism groups. That is, something like this can be done, but mathematically at this moment is very difficult because the structure of this group is complicated. Even with measure like integration is not well defined in many cases. That is, this is only a future, but in principle, I think it's possible. Another comment about result which we got here, namely this calculation of variance and similar things that we get that both explodes are related to Heisenberg uncertainty principle.
Yes.
It means that more or less one can conclude that this uncertainty principle prevents to hitting the singularity, because probability of finding such state is zero. As usually in quantum mechanics, all is possible, but it depends how large probability is. Here, probability is zero. That is, in this sense, we can now say that uncertainty principle prevents against obtaining singularity in such models. And it is not due to dynamics, but in fact due to structure of and geometrical behavior of observables, like time in this case and position.
Can I comment?
Yeah,
sure.
Hi. So let me first make a general comment. I would like to contrast this program with say, loop quantum cosmology. So in case of loop quantum cosmology, we start with a general quantum theory, and then loop quantum cosmology is, well, it's a set of models which are sort of toy models, but for the general theory. So in this sense, well, they're even not approximations. This is some difficult mathematical subject. We always try to prove that those models in fact approximate the general theory. However, they at least are attempts to approximate this general theory. On the other hand, in this project, you seem not to worry about any general theory that would cover all gravity. You just say your strategy is you give me an exact solution to Einstein equations, and I will come up with some suitable quantization procedure. So I think that from intellectual point of view, it is interesting, but I don't see any deep reason why such quantization makes physical sense. So what if we didn't have this classical theory? So this is one of comments which Professor Trautmann always make whenever some string theory people come and say, "Oh wow, we have derivation of quantum Schwarzschild spacetime," but always the derivation begins with writing the classical formula for Schwarzschild, and then there are some procedures, and then this Professor Trautmann's comment is, ha ha ha, so, but we needed the Schwarzschild metric first, and then given the Schwarzschild metric, we implement our theory. Try without the Schwarzschild metric, and then let the Schwarzschild metric appears magically from your theory as one of the examples. So this is my general skepticism. I have also technical questions, but maybe you want to answer.
Okay, so let me reply to the first one. Well, this is definitely bottom-up approach, let's say, not top-down, but bottom-up. So this is not the end of the story, just beginning of this the development of this quantization scheme. Maybe at the end we'll find general formulation, but we just want to, to do something which is, I mean, yes, this is just this direction, bottom-up. You are right. It's completely different approach. But the one advantage I would say, comparing to canonical quantization, is that we are not afraid of any form of observables. It needn't be, polynomial type. You can give me almost any classical observable, and I am able to ascribe to it quantum operator. That's I don't need to worry about order of operators. Sequence of describing about the sequence of operators. That's the main advantage. And this method is highly flexible due to this. There are many items which can be. So it's nice when you have a possibility to ascribe, theory to reality, because usually reality is complicated, and if you have read theory, you just can immediately, finish your program very quickly. Here it is very flexible. That's another advantage of this approach. But obviously, it has many disadvantages as well, as usually. I don't claim that this is the best one can imagine. I spent 7 years applying loop gravity approach to cosmology, and now I spend almost the same amount of time, applying this method. And maybe, and I'm not saying that any of this is, the best one can imagine. Maybe one day people will find still another approach. This is interesting to have something new. Okay.
Next. Can I ask more technical, detailed questions? So it seems to me that one of the main elements of your quantization is to identify a classical variable, which in classical theory takes only real values, so it is bounded by 0 from below. And then you use your group of transformations. However, well, if you consider the Kerr spacetime, for instance, in that case, the R variable ranges from -infinity to +infinity. So it seems that there is no easy extension of this. So in other words, you have to go case by case, and in each case you have to come up with some different quantization scheme.
Sorry. No, you can use other group. It's Heisenberg group in this case.
Yes.
Simply.
Because it's group quantization.
It depends on structure. Quantization is dependent on structure of your configuration space. Which kind of group you can use.
Yes.
But scheme is exactly the same.
Yes.
But I understand your objection about, I can say, thinking from what point we should start. You think that at first we should construct quantum approach, and from quantum approach, trying to see if it is, as in quantum loop method, as we see if it can describe really general relativity. This is obviously much better, but historically, even in quantum mechanics, you will have such an approach that we try to find analogy between classical and quantum, and finally we learned how to construct quantum operators in many cases. Here is also this kind of knowledge which we can get.
And what is the meaning of this group which you introduce?
This is, we say, you have, let's, for instance, here configuration space, and you ascribe, you try to describe to it a group structure, and such a group which has representation, irreducible unitary. So as Andrei said, each case is in a sense different because you start from configuration space, or let's say phase space, and you try to ascribe to it a group structure. Okay, so if you define the multiplication on this, you have group structure. Okay.
I can add that they simply generate the state space, Hilbert space, for appropriate configuration space, classical configuration space. Yes. This is what is needed.
Yes, yes. So you need this unitary reducible representation on a certain Hilbert space to play the game with this coherent states. But if you have this, you have immediately Hilbert space. You don't need to worry. You have Hilbert space. So that's
because always in quantization you have two problems. First is not to get operator, but operator has to work in some space.
Yes, yes.
That is, this structure, this group supplies such a structure like Hilbert space for given configuration, classical configuration space.
Yes.
Perhaps you mentioned that in the beginning, but now I would like to go back to this. So what if I describe Schwarzschild spacetime in terms of Kruskal coordinates? Then what do you do?
Well, we haven't tried that because that would be, let's say, another next step. Because in that case we can, that's another. Yes. Here, let me come back. So we use the simplest possible. Traditional Schwarzschild coordinates, okay? But as you said, I can use, different coordinates, for instance, Kruskal-Sekeres. We haven't tried that, but it's obvious next step. I mean, this project can be developed in many directions. So this is the simplest possible.
And can we go back to this issue of physical dimensions? So
Yes.
so R and T in Schwarzschild spacetime, as you seem to
Yes.
to be using them, they should have dimensions of length, centimeter.
Yes.
And in order to turn them into dimensionless variables, you need to, well, use some parameter, for instance, mass. I don't know. So what do you specifically do?
Here, it's nothing special, I would say. I don't need to worry. I mean, velocity of light equals 1, capital G. Not this one, but I mean this.
For example, you can use Planck length for this. Doesn't matter.
For instance, yes, you can use Planck length.
Doesn't matter which one. Yes. Structure is dependent on this.
But you choose, say, T and R are coordinates, and you say that they are dimensionless. But it means at the same time that you have some constant of dimension of the length in the metric terms. So you always can move the dimension from coordinates to coefficients of the metric tensor, or the contrary. Yeah. So in any case, you need some constant of dimension. Otherwise, the measure of distance doesn't make sense. Yeah?
Yes, but the choice of units is arbitrary totally.
No, okay, but it means you choose some.
Yes, but it's fixed for the whole, for calculations, for theory, simply fixed for all values which we need, where it's something.
But, okay, like but you have to, you should somehow show that all results are independent of the choice of the constant. Probably they are independent, but formally it should be shown.
Yeah, no, here you have spaces which are uniform, because group spaces are uniform. That is, in this sense, scaling is unimportant, in fact.
Yeah.
No.
I think it would be easy. Yeah, so.
No.
Formally, there is a problem, but practically, maybe.
I think so.
No problem.
So maybe I will make another comment, namely that, resolving, I mean, let's say resolving singularities based on the quantization of scalar curvatures. Scalar curvature is not the end of the story, I would say, because there are many scalar curvatures. Recently, I've seen a paper in which they consider 17 scalar invariants. Okay, so maybe a better approach would be to quantize evolution equation for the expansion of congruences. Okay, congruence. So in a sense, quantization of it's difficult to pronounce, Reicha-Hund-Hurry's equation. And in fact, this will be a talk given by Sauria Das in April 29th, okay? And especially I invited him for that purpose. This will be more general approach, addressing all singularities in one go.
So can I give a comment?
Yes, please. Sure, but I think we should be closing shortly. Yes, but please go ahead.
Okay, so let me quick. So classically, we have this manifold, and under manifold we have coordinate. Once we choose a coordinate, the field can be expressed as a function of the coordinate. And in quantum field theory, and also in, for instance, loop quantum gravity theory, So what we really quantized is actually the field itself rather than the coordinate. But in your approach, it seems like that what you really quantized is actually the coordinate. And of course, if we regard this coordinate as some reference as some reference field, so then what you really quantized is actually this reference field rather than the gravitational field. So from this point of view, it seems like you didn't quantize this gravitational field.
Yeah, I would say, I mean, this is just, you know, beginning of the game, I would say. I believe that, you know, development of this approach will touch also, could also deal with fields, directly with fields. Anyway, this is just the beginning of the game.
Yeah, okay.
All right, so I think at this point we can thank the speaker again. And I would ask the people who might be interested in organizing the next Potter meeting to stay with me and with Włodek